This is 2023-0079 Kim Dong-uk, and I'm gonna talk about calculating the shape of Earth. What do you think shape of Earth is? Many people think, and as usual, we use sphere model for Earth. We use sphere model for calculating many problems in classical mechanics because it reduces calculations of calculating the gravity. Because of Newton's shell theorem, we can easily calculate gravity of sphere Earth. And some people in today claims that Earth is flat, but we know that this is not the case because if the Earth is flat and gravity is very uniform, as you can see in Gauss' theorem, and this is not true. But in reality, Earth is not a sphere. Earth is more like a sphere like ellipsoid, and we call it the oblate spheroid. And it has semi-axis of A equals 6,378 kilometers, and B, the small semi-axis is 6,356 kilometer. And I'm gonna talk about the history of calculating the shape of the Earth. Isaac Newton claims that Earth is the oblate sphere. He was correct, but he didn't actually calculated the eccentricity of the Earth. And later, Maclaurin, who is famous for Maclaurin series, calculated the eccentricity of Earth with Earth's rotating angular velocity, omega, and he assumed the planet as a fluid with constant density, and he used hydrostatic equilibrium condition to obtain the following expression, which is stated in PPT file. And today we're gonna derive this relation, but not the case with Maclaurin's derivation, and we're gonna derive this expression with energy condition. To use the energy method of deriving the eccentricity of Earth, we should first know that centrifugal force of the Earth. Because Earth is rotating, we need to consider additional force due to rotation. This is because that if we think of the Earth's rotating frame, and rotating Earth's frame is not an inertial frame, so we need to consider the inertial force, the pseudo force. And note that we are not gonna derive the non-inertial force due to rotation, but we're gonna simply use the results that derived before, and I'm gonna state that results that we have Coriolis force and centrifugal force, and we're only gonna use centrifugal force because this is equilibrium case and there is no particle with speed, so we only need to consider centrifugal force. And note that centrifugal force is conservative because if we take the curl of the centrifugal force, and it results 0. And let's calculate the energy. We can think about two energies, and first energy is energy due to gravitational potential energy, energy due to gravitation, and we denote it by Eg. And there is another energy, which is centrifugal potential energy, which is due to centrifugal force. And here we know that the curl of the centrifugal force is 0, so we can define the centrifugal energy. And E is eccentricity. So if we take the derivatives of total energy respect to E, and if we find the minimum condition respect to E, and we can find the eccentricity of Earth because we know that energy is always minimized when it is equilibrium condition. To calculate the minimum of energy, we need to express the energy with eccentricity. To simplify the calculation, we introduce the new coordinates. This coordinate is very useful when we deal with oblate spherical objects. And there is eta, and there is psi and phi, and xyz is converted with psi, eta, phi, with relation stated in left. And there is a scale factor which is derivatives of psi, eta, and phi. The derivatives of r respect to psi, theta, and phi, uh, psi, theta, and eta, and scale factor is stated as left. You can easily derive this scale factor with some elementary calculations. And we'll now gonna calculate the gravitational potential energy. Gravitational potential energy of Earth is U, and we use the U, and this left U and right U is different, and we're gonna calculate the right U. And right U is G rho squared divided by 2, and this integral. And this is obvious because we double count the uh, potential between two particles. So we divided it by 2, and the minus sign is concluded in in the above expression, so we don't consider minus sign, and minus sign will be there at the last. So changing the coordinates to psi, eta, and phi, we get next expression, and we're gonna use the we're gonna use that infinite sum of Lysander polynomial, first kind of Lysander polynomial Pn, and second kind of Lysander polynomial Qn, and we can express the 1 over R1 minus R2 with this kind of expression. If you're interested in derivation of this expression, you can notice you can note that any kind of mathematical physics books can have this kind of derivation. And further calculating this expression with more mathematics, we use the fact that Lysander polynomials are also orthonormal, and we do the calculation by this slide. And if you're interested in this slide, you can look at it. And finally, we get UE equals 3gm squared divided by 5r times 1 minus e squared power 1 over 6 and sine inverse e divided by e. And let's look at the centrifugal potential energy. We already calculated the gravitational potential energy, and we're going to look at centrifugal potential energy. If we let's derive the expression of the centrifugal potential energy. If we assume that omega is omega z hat, and z hat is the unit vector along the z-axis, without loss of generality, because a simplification of calculation because of that, because cross product and the gradient is a vector, so we can easily show omega squared rx x hat plus ry hat is minus gradient minus 1 over 2m rx squared plus ry squared omega squared. So centrifugal potential energy for many particle system is minus 1 over 2I omega squared. Here I is inertia. So we can also calculate the inertia and psi 0 with eccentricity, and we can calculate the E omega, the centrifugal potential energy, respect to E. And we can now take a sum of the two energy, and we can calculate the total energy. And total energy is kind of complex expression, so we substitute the 3gm squared divided by 5r and omega squared mr squared divided by phi as a and b. And we can simplify the expression, and we can take the derivative respect to E of the total energy. We get the local minimum, which is minimum of the total energy, and we get the eccentricity expression with omega. And it is written here. So if this expression is so complex, so we cannot solve it by hand. And if we put the actual value of low, the average low, and omega, and we can calculate the eccentricity numerically, and we get 0.092. But observed E is 0.081, so it's not really matched, so there is error. We can do error correction. The error is due to the naive calculation of inertia. And we can calculate the inertia, and everybody for the real Earth, the close to real Earth, because everybody knows that Earth has core and mantle and that kind of thing. And we calculate the inertia one more time by assuming the two level model of Earth, the core and mantle, and we can do the calculation we do previous, and we calculate the fixed eccentricity of Earth, and that is 0.086 with this inertia. And here we assume that Earth is sphere because calculating the eccentricity of the oblate spheroid is really complex if the case of two layer. So we calculate again, and it is 0.086, and this is close to the real world eccentricity, and by 5.5%, and this is satisfactory. For further discussion, the omega squared and eccentricity has this relation as we derived before. And in case of E is very small, E is reduced by some kind of Taylor expansion, and uh, we can reduce this expression to E equals omega times squared 15 divided by a pi rho g. And this means that eccentricity and the angular velocity are in linear dependence. And in real case, Mercury and Venus has very long rotation periods, which means that omega is very small. And in real life, the Mercury and Venus has very small eccentricity. It is close to sphere, which matches our intuition, and it concludes that this expression is correct. Thank you for listening.